We've spent a considerable amount of time in this course using Gauss-Jordan and Gaussian elimination to solve systems of linear equations. We've seen how this can take quite a long time, especially when doing it by hand. Today we're going to introduce a more advanced way of solving systems of linear equations that involves factoring the coefficient matrix into a product of triangular matrices. It's called an LU decomposition. And here's the definition: a factorization of a square matrix A into A equals L times U, where L is a lower triangular matrix and U is an upper triangular matrix, is called an LU decomposition or LU factorization of the matrix A. In this video, we'll go over how to find these LU decompositions, but first, I think it will be helpful to motivate this by seeing how they can be used to solve systems of linear equations. Here's the process, which is quite clever. To solve an n by n linear system ax equals b using LU decomposition, we follow these three steps. Note, by an n by n linear system, we mean n equations in n unknowns. So the coefficient matrix A would be n by n. The first step is to use the factorization A equals L times U to rewrite the equation AX equals B as LU times X equals B. So just replace A in this equation with L times U. Then we make a variable substitution. U times X is a 3x1 vector. We're going to call that vector Y. So now Y is like a brand new variable vector, and we're going to replace UX in this equation with that new variable vector y. In this way, we get a new system where y is the variable vector, we have ly equals b, and we can solve this for y. This is easy to solve because the coefficient matrix in this new system is lower triangular. Once we solve this system for y, we can come back to this equation, y equals ux, plug in the known values for those variables in the vector y, and then solve this system for x. Again, this will be easy because the coefficient matrix is upper triangular. As you can see with this method, instead of solving one system, ax equals b, we solve two systems, ly equals b and ux equals y, which are both easy to solve because they have triangular coefficient matrices. For an example of this method in action, before we see how to construct these LU decompositions, consider this system. A times x equals b. It is a 3x3 system. Now you'll have to trust me on this. The matrix A equals L times U. So we're going to just take this factorization for granted. We'll find our own LU decomposition of this matrix later. Let's refer back to our steps. Step 1 is to use the decomposition to rewrite the system. So indeed, we'll replace A in this system with L times U. Then we get this equation. L times U times the variable vector x equals the constant vector. Then step 2 is to use this equation, ux equals y, so we have this new variable vector y, in order to rewrite this equation. So you can see we have u times x in that first equation, and we're going to replace it with this equal variable vector called y. Thus, we get this equation. This is L, the lower triangular matrix. This is y, which is replacing u times x, and then there's our constant vector, b. And now we have to solve this system. You're probably familiar with solving systems when the coefficient matrix is upper triangular. We perform Gaussian elimination to get in that situation, and then you use a process called back substitution. In this case, the coefficient matrix is lower triangular, so we actually have to use something called forward substitution, but it feels more or less the same. The first equation is giving us a definite value for y1, so we plug that into the second equation, and that will let us solve for y2, and then we can plug everything into the third equation to solve for y3. And you can see that process here. The first row tells us that y1 equals 2, and then we plug that into the second equation, which tells us that 2 times 2, which is 4, plus y2 must equal 2, and so y2 equals -2. And then plug those known values for y2 and y1 into the third equation, and we solve for y3 and find it equals 10. So now we know what y1, y2, and y3 are in this variable vector. We can replace these variables now in this equation and then solve it for x. So using that equation, ux equals y, and replacing y with all those known values, we solve this using back substitution because the coefficient matrix is upper triangular. The third equation lets us solve for x3. It gives us that x3 equals 5. We plug that into the second equation, which tells us that x2 minus 5 equals -2, so x2 equals 3. And then we can plug that value for x3 into the equation, which comes from row 1, and solve for x1 and find that it equals -1. If any of this process is unknown to you, be sure to check out my videos on Gaussian elimination. Links in the description. So that's how LU decomposition can be used to solve a system of linear equations. Now, as we'll see, to construct one of these LU decompositions, it's actually necessary to perform Gaussian elimination on the coefficient matrix. So you may wonder, what's the point then? If we have to use Gaussian elimination anyways, just to start using this method, why not just solve the system with Gaussian elimination? Well, the thing is, to solve the system with Gaussian elimination, you need to consider the effects of the row operations on the constant vector b. However, the LU decomposition is totally independent of the constant vector. It has to do only with a. Since the LU decomposition is independent of the constant vector, you can use that decomposition to solve a sequence of systems that all have A as their coefficient matrix. A sequence like this, where the coefficient matrix is fixed, but the constant vector varies. The LU decomposition of A will be valid for every one of these systems, and so you can take advantage of it many times, thus in the long run, saving a lot of time. A situation like this arises naturally when the coefficient matrix is fixed, but the constant vector is varying. For example, it may vary over time. The coefficient matrix stays the same, but the constant vectors could change, and you could use that same LU decomposition to solve all these systems very easily. Unfortunately, not every matrix has an LU decomposition, but this theorem will tell us a particular situation where we can always find an LU decomposition, and in proving this theorem, we'll begin to see the process necessary to find these decompositions. The theorem states, if A is a square matrix that can be reduced to a row echelon form U through Gaussian elimination without swapping rows, then A can be factored as A equals L times U, where L is lower triangular and U is upper triangular. Note that we're calling the row echelon form of A U, because the row echelon form is an upper triangular matrix. It has to be, by definition of row echelon form. And as it so happens, that's exactly the upper triangular matrix that we will use in an LU decomposition. Now, beginning the proof, remember we're assuming that A is a square matrix that can be reduced to row echelon form through Gaussian elimination, but without swapping rows. Now, that Gaussian elimination is a sequence of elementary row operations, and each elementary row operation can be carried out by multiplying by an appropriate elementary matrix. Link in the description to my lesson on elementary matrices if you need to review. So we can view that Gaussian elimination as an equation like this: the matrix A multiplied by all these elementary matrices which carry out the necessary elementary row operations to reduce A to U. This product equals U. And elementary matrices are invertible, so we can actually solve this equation for A and find that A is equal to U multiplied on the left by the product of the inverses of those elementary matrices which were used to reduce A to U. To make sure that's clear, to solve this equation for A, we'd have to multiply on the left by EK inverse, which you see there, and then we'd multiply on the left by the next elementary matrix inverse, and so on. Eventually, we'd multiply by E2 inverse, and then finally, we'd multiply by E1 inverse, and that's how we solve for A. Now, this product of inverse elementary matrices is in fact the lower triangular matrix L that we need for our decomposition. Now, we see clearly that A can be written as this, which we're calling L, times this matrix U. So all that remains to be proven is that L is lower triangular and U is upper triangular. We pretty much already explained why U is upper triangular. That's because it's in row echelon form, which by definition is an upper triangular matrix. Remember, U just comes from the hypothesis of the theorem that A can be reduced to row echelon form specifically without swapping rows. So U is upper triangular, and L is lower triangular for a more complicated sequence of reasoning, but let's go through it. Firstly, since row swaps are excluded, each elementary matrix EI results from either adding a scalar multiple of one row of an identity matrix to a row below, that would be done to introduce zeros below leading ones, or from multiplying one row of an identity matrix by a non-zero scalar, which would be done to introduce leading ones. Remember where elementary matrices come from. They come from performing a single row operation on an identity matrix. So this is describing all possible elementary matrices that could be in this sequence. Since row swaps are prohibited, this covers all possible elementary matrices. And remember, an identity matrix is a diagonal matrix, and it's also technically lower triangular. And what this describes is that the identity matrix either just has a row multiplied by a non-zero scalar, which won't make it not lower triangular, or what is done is a multiple of one row is added to a row below it, which will also preserve the fact that it's lower triangular, because stuff's being moved below the diagonal. Hence, all of these elementary matrices are lower triangular. Since each elementary matrix EI is lower triangular, just by the nature of where they must come from, we know that each inverse, EI inverse, is also lower triangular. We've previously proven that the inverse of a lower triangular matrix is also lower triangular. I'll leave a link in the description. And also, their products are lower triangular as well. If you multiply lower triangular matrices together, you get a lower triangular matrix. Link in the description to the video where we prove that. And so indeed, this product of inverses of lower triangular matrices, which we're calling L, is itself a lower triangular matrix. And from this proof, hopefully you can start to see the process necessary for finding an LU decomposition. We must perform Gaussian elimination on the matrix A to get the upper triangular matrix U, and then, in a way, we're just multiplying the inverses of the elementary row operations that we used on A. We have to multiply the inverses of those together in order to get L. Let's see an example. Here's pretty much the whole process, which just barely fits on screen at once. We start with the matrix A, and we perform a sequence of steps, elementary row operations, in order to reduce it to row echelon form. And this row echelon form is our upper triangular matrix U. Now, each of the row operations that we have to carry out have a corresponding elementary matrix representing that row operation. And we know it's the inverses of these elementary matrices, which will be necessary to get the lower triangular matrix L. In fact, we just have to multiply all of these together from top to bottom to produce L. Just quickly going through these steps, we first multiply row 1 by a third to get a leading 1. The elementary matrix that represents that has 1/3 in that leading entry of row 1, and its inverse has the reciprocal of 1/3, which is 3, in that leading entry. We then subtract 6 row 1 from row 2 in order to get a 0 below that leading 1. The elementary matrix corresponding to this has a -6 in that row 2 column 1 entry, and its inverse has the opposite, +6, in that row 2 column 1 entry. We then add 3 row 1 to row 3 in order to get rid of this -3 to finish getting zeros below the leading 1. The corresponding elementary matrix has a 3 in that position where we made the change, and the inverse has the -3 in that position where the change was made. Finally, we subtract row 2 from row 3 to get a 0 below that leading 1, and we see that there. The corresponding elementary matrix has a -1 where we made that change, and its inverse has the opposite, a +1 where we made that change. Note how the inverse elementary matrix will have a reciprocal if all we did was multiply a row by a scalar, and it will have a negative if what we did was subtract subtract or add a scalar multiple of one row to another. So from all of this, we have that this is the upper triangular matrix, and then L, as we said, is just the product of all of those inverse elementary matrices. This is the inverse of the first elementary matrix. This is the inverse of the second elementary matrix, and so on. And you can verify that this product produces this lower triangular matrix. And finally, we see that the original matrix A can be factored into this matrix L times this matrix U. You can verify this multiplication is correct if you like, but that is an LU decomposition of A. And note, this matrix A is the same matrix we worked with at the start of the video. However, this is a different decomposition, and so from this we see that LU decompositions are in fact not unique. This is the LU decomposition we just constructed, and this is another LU decomposition for the same exact matrix. Now you may be thinking, yikes, that's a lot of work. But it's not nearly as bad as it looks. Really, all we have to do is this Gaussian elimination. The rest is really easy. And that's because it's super easy to convert these row operations into our lower triangular matrix L. So in practice, all of this matrix multiplication and these inverse matrices, not actually necessary. Just look how straightforward this correspondence is. The first thing we do is multiply row 1 by 1/3 to make this entry a leading 1. And so, in the lower triangular matrix L, we put the reciprocal of 1/3, which is 3. The next thing we do is subtract 6 row 1 from row 2 so that this entry becomes a 0. So in that position, in L, we'll have the opposite of -6, which is positive 6. Now again, I want to point out, if we're just multiplying a row by a scalar, that's when we see reciprocals in L. But if we're adding a scalar multiple of one row to another, that's when we see negatives in L. So the next step is adding 3 row 1 to row 3 so that this entry becomes a 0. So in that position in L, we should have the negative of 3, which is -3. And then finally, subtract row 2 from row 3 to get a 0 in that position. So we'll have the opposite of -1, which is +1 in that position in L. That's how easy it is to construct L, and here those steps are written out with a little bit more formality. To construct an LU decomposition, first, we reduce A to row echelon form U through Gaussian elimination without using any row swaps, and we have to keep track of the multipliers that are used to introduce the leading ones, and the multipliers used to introduce zeros below the leading ones. The multipliers that are used to introduce leading ones are just multiplying rows by scalars. That's when we would put reciprocals in L. And the multipliers used to introduce zeros below the leading ones come from adding multiples of one row to another. That's when we would use negatives in L. So step 2, in each diagonal entry of L, write the reciprocal of the multiplier used to introduce the leading one in that position in U. Again, this is just in the diagonal entries because that's where these multipliers are used to introduce leading ones. For step 3, in each position below the diagonal, we're going to write the negative of the multiplier that was used to introduce the 0 in that position in U. And for step 4, we now have L, we now have U, so we can form the decomposition A equals LU. Let's finish by walking through an example using those steps. We're going to find an LU decomposition of this matrix, and I encourage you to give it a try yourself before watching me walk through it. Here is our matrix, we'll just call it A for convenience, and here is the matrix L, where, it's lower triangular, so we know these have to be zeros, and all of these entries with the dots are yet to be determined. To begin Gaussian elimination, we want to multiply row 1 by 1/2 in order to get a leading 1 there. So we need to put the reciprocal of 1/2 in our matrix L. Thus, in that entry, we're going to have 2. Again, this 1/2 was done in order to change this entry to a 1. So it's the corresponding entry in L, which we hit with the reciprocal of 2. Then we need to do two things. Subtract 4 row 1 from row 2 to get a 0 there, and subtract 1 row 1 from row 3 to get a 0 there. Since we subtracted 4 row 1 from row 2 to change that to a 0, in L, we need to replace that corresponding position with the opposite of -4, which is +4. Since we subtracted one row 1 from row 3 to get a 0 in that position, in that same position in L, we need to use the opposite of -1, which is +1. Then we multiply row 2 by 1/9 in order to get a leading 1 there. So in that corresponding position of L, we put the reciprocal of 1/9, which is 9. Again, this is when we use reciprocals rather than negatives, is when it's just a single row getting multiplied by a scalar to introduce a leading 1 on the diagonal. Then we'll subtract 3 copies of row 2 from row 3 in order to get a 0 below the leading 1. So since we subtracted 3 copies of row 2 from row 3 to change that entry, in that same position we'll put the opposite of -3 in L, which is +3. Finally, we're going to multiply row 3 by 2 to get a leading 1. And so, in that same position where we're making the change, in L we'll put the reciprocal of 2, which is 1/2. Now we have L, and having completed Gaussian elimination, we have U as well. And thus we can form the decomposition A equals L multiplied by U. We've written A as a product of a lower triangular and upper triangular matrix. I'll leave a link in the description to a video where we use this decomposition in order to solve a system of linear equations, so check that out if you're interested. But that's an introduction to LU decomposition, where it comes from, and how it's used. Let me know in the comments if you have any questions, and be sure to check out my linear algebra course and linear algebra exercises playlists in the description for more. If you find my videos helpful, please consider supporting what I do by joining Wrath of Math as a channel member. You can get early and exclusive access to additional videos and extra practice, and if you join at the premium tier or above, you can access the lecture notes used in this course. Thanks for watching.